All right. Today we are going to add a concept. It's going to seem like a new idea. I'll tie it into some other ideas. Today is May 14th, 2013, and we are going to start talking about the derivative and see how far we get. Okay? So we're talking about the derivative. New word, new concept. I'm going to put a general graph up here. This is some function, okay? This is the most important idea for calculus right here. And we're going to start talking about what this means. And we're going to bring together a lot of the concepts we talked about in the last section and this one all today. Here's just some function. Don't particularly care what it is. I'm just going to tell you it is a function. Okay, passes the vertical line test, only one y for every x, etc., etc. Now, you have heard all this before, my friend. Okay. Between any 2 points on this function, we may draw a line. And if we do, we call that line a secant line. Anyone know what secant means? Anyone taking Latin in here?
Yeah.
Okay, do you know what secant means?
We knew what tangent meant.
All right, we talked about tangent earlier. Secant means, I didn't really mean to look it up. Secant means sever. It means sever. It's the same root as like shortcut. You're cutting across the function.
Yeah, that makes sense.
Okay? And if you want, what you can do is find the slope of this secant line. And the slope will start here at this x value, will wind up over here somewhere, and if you guys remember this symbol, delta x, remember what that means?
Change of distance.
Change of x, change of horizontal distance. Excellent, Remy. So this is your change in x, which means if I start here at some x point, okay, when I'm done changing x, the place where I wind up is a new x point. What x point is that? It's whatever this x value is, plus however much change I added. So this is x plus some more x. So we're going from x to x plus some more x. This is just Algebra 1 sort of rephrased. Okay? Any questions on what I've done so far? We go from x by a distance of delta x, and if we jump from this point to this point on our function, we are tracing what's called a secant line. Now every x on a function has one corresponding y. Exactly one. It's really the definition of a function. You go above or below some x point, you only hit y once. So we say f of x is the y value that corresponds to x. This is not a trick question. It's going to sound like it. If I have x corresponding to f of x, how would I write the y value that corresponds to x plus delta x? Take x, this is f of x. If this were 2, this would be f of 2. If x was 5, this would be f of 5. If x was helicopter, this would be f of helicopter.
So that's f of helicopter plus more helicopter.
Alright, wow, you rolled with that very quickly, Danny.
I did.
So, in other words, if you take whatever's here, put it in here. So this y value up here, how would I write it in terms of this?
It would be f of x plus delta x?
Yes. Yes, it would be. Okay, so right now we're just doing new vocabulary. These are really Algebra 1 ideas, but I'm just layering a little calculus vocabulary onto them. Alright? So that's f of x plus delta x up there. Now, what would the slope of this secant line be? M sub secant. Well, what's slope in general? What slope formula did Algebra 1 kids learn how to rattle off the...
Y equals mx plus b?
That slope-intercept form
That's
of the
not
line.
perfect, wait a minute.
What's a formula for
Wow.
just the slope part?
Rise over run.
Rise over run, that's one of the words of it.
X over fx.
You got it upside down and you're leaving a part out. You're leaving the change part out. I've seen
Well,
delta y over delta x, right?
Mm-hmm.
I hope you guys won't feel embarrassed in a minute. Please tell me you guys saw y2 minus
Yeah,
y1
yeah.
over x2 minus
Mhm.
x1 at some point, and just were forgetting the
Yeah.
vocabulary. But I'm asking you, I'm
And
giving you a
that's
question.
rise over run.
And this is the same thing as rise over run. Okay? But using this notation, I could also write it as, y sub 2 here, I could call my f of x plus delta x. Y sub 1 I could call my f of x. And then in my denominator, my change is just this distance between the two x's. That's my run. So all I have to write on the bottom is delta x. You guys good with that? Okay? There's another word besides rise over run. There's another English translation of slope that you don't hear enough in math, that kids don't hear enough and aren't reminded of it. And that is average rate of change. That's another way to put it. Average rate of change. Okay? Now, I'm going to put a sign up real quick when I do this. Average rate of change, what does that mean?
That's the average of how it changes, or the rate that it changes at?
Yeah. Average rate of change is what you guys have been finding for years in Algebra 1 classes and science classes without really thinking of it in that terms. For example, you guys did a lot of problems with things like, what am I thinking of? A car drives 6 hours at 50 miles an hour. 6 hours at 50 miles an hour. How far has that car gone? If you do 6 hours,
Yeah, 6 hours at 60 miles per
I
hour?
would say 50 miles an
50
hour.
miles an hour?
So you multiply, what would you do?
Multiply 60 by 50.
6
and-
times 50.
Well, 6 times 50, and
Right.
then you get the average of, then you divide it again.
Well, that's if you
Divide
wanted the
again.
average. Okay, you're jumping ahead. You're
Yeah.
doing a lot of things today. They're all right, but if you just said you did a lot of problems starting in middle school, I hoped, where if a car went 50 miles an hour for 6 hours, it went 300 miles.
Yeah.
You guys remember those? But the idea behind that is the car goes exactly 50 miles an hour. It doesn't slow down. It doesn't stop. It doesn't hit a tree. The driver doesn't brake for anything. The driver never stops to go to the bathroom. That's your average rate of change, and it's not a very precise or often useful way to talk about what's actually going on. Sometimes we want to know what happens when a car hits a tree. We don't want to know the average. We want to know what's happening right in that instant, right at that moment of impact. So in physics, we talked a little bit about instantaneous rate of change, but we didn't really say how to find it. Okay? A slope of a tangent line will tell you an average rate of change. Okay? How do we find an instantaneous rate of change? Well, here's a problem. I'm going to switch colors for this. I want to know exactly what's happening at that point. I don't want to know what happened from here to here. I want to know what's happening at this point where I don't have a tangent line. I don't have a secant line, excuse me. I have a tangent line. And what is tangent Latin for?
Touch.
Touch. Tangent is Latin for touch. I don't want to cut across. I want to touch right at that point. I don't want to sever. Okay? So there's a slight problem with this. The tangent line is only above one x value, and it only corresponds to one y value. So I'm going to do something here that, and then I may have to keep, I have to try and do 2 boards today. So here's the quick problem. If I look for the slope of a tangent line, the first thing I get is I get a y minus the same y, I've only got one y value, divided by an x minus an x. And it's the same x value. This is like saying y sub 1 minus y sub 1 over x sub 1 minus x sub 1. So what's the problem with that?
That's
It's undefined.
Mhm.
Remember, we went over these words about 2 weeks ago, Remy.
Oh no.
Undefined
It's-
would be 0 on the bottom,
It's gonna be
Or
on
it
the
would be
top.
0 on the bottom.
but it'll also be 0 on the
It's
top.
gonna be 1.
No, it's not one. We had this
Wait,
conversation.
No, wait.
This was the, we called this an indeterminate
Oh,
form.
I feel so stupid.
Don't feel stupid. You are a little bit of a random math vocabulary generator today, Danny, I won't lie.
I am.
But, no, undefined is a smart mistake, Remy. Because 0 on the bottom, you've been told about that. And Danny, you have been told over and over, anything over itself is 1.
Yeah.
But 0 ruins this. So I'm going to quickly go over indeterminate form again. Over on the other board. The picture won't be as good, but we talked about this a little bit before. If I have 0 divided by 5 equals blank, okay? If I have 0 divided by 5 equals blank. This is a division problem. It can always be rewritten as a multiplication problem, and the multiplication problem is blank times 5 equals 0. What works there? What makes that statement true?
Have you multiplied by 0?
Well, I've got 0 divided by 5 equals blank.
0.
0 works, right?
Yeah.
Okay, so 0 on top of a fraction, no problem. You just get 0. Because if you rearrange it as multiplication, the answer seems, I hope, fairly evident at this point in your math careers.
Yeah.
0 on the bottom really isn't any more problematic. 5 divided by 0 equals blank can also be rewritten as a multiplication problem. And the multiplication problem would be blank times 0 gets you 5. And believe it or not, this has an equally simple answer. What can I multiply by 5 and wind up with 0? I'm sorry, yeah, what can I multiply by 0 and end up with 5?
Nothing.
Nothing. Nothing. There is not a damn thing that we can do here.
Yeah, this is weird because they always say if you flip this stuff around,
Mhm.
you can always find you can't the 0.
Well, with this one, I mean, this is a clear answer. Like, don't mistake this for, like, anything more than it is. People start to think undefined is profound, but it's a really simple answer. The answer is there's nothing you can do. It's about as clear an answer as you can get in math. We call this undefined because we cannot define a mathematical concept, expression, number, or idea that you can multiply by nothing and get a number. Okay? But there's nothing wrong with that. Undefined is fine.
Wait, but 0 divided by 5 divided by 0 is undefined, right?
5 divided by 0 gets you undefined. That's where I should have written it. Okay? 0 divided by 5, no problem. It's 0. Not a worry at all. 5 divided by 0, no problem, it's undefined. If you're looking at a rational expression, you've got a vertical asymptote. Function doesn't exist there. A couple of complicated rules. This one, though, 0 divided by 0. And we went over this briefly with removable discontinuities a few weeks ago. But I decided not to give you one of those on the exam. 0 divided by 0 equals blank can be rewritten as blank times 0 equals 0. So the answer to this division problem is going to be whatever makes this statement true. And what makes this statement
0.
true?
Or any number. It can be anything.
Anything. Anything. And the mathematical term for anything is indeterminate form. It's not really the mathematical word for anything, but it works for our purposes. There are a couple of other indeterminate forms. Infinity over infinity is similarly problematic.
Well, wouldn't you just...
It's
Well, with
not one.
but with that, it's like, I guess, because infinity keeps on going.
Right.
And if you divide it, keep on going, but keep on going, wouldn't you?
Well, actually what happens is sometimes it's a race and sometimes the top or bottom way. Depends on
I
what
guess
expression.
that's a good point.
And
But
this
they're
is
both
where...
moving at the same, I don't want to misuse rate, but I'm going to use it anyway.
No, go ahead. It's
They're
good.
both moving at the same rate, and you divide them, they're gonna wouldn't they both be 1 because they both be at the same number?
Have we looked at an example of this by any chance?
Don't think so.
Really? Because I was thinking we looked at some rational expressions
I mean,
where
it's
we had
possible.
like 5, remember it looked like 5x squared plus 3x plus 7. Quick example here.
Oh, maybe we have.
And if I divide that by 2x squared plus 3, and if I say what's the end behavior of this function, what Remy was very good at, as I recall, is if we take the limit as x approaches infinity, okay? Now remember when I said a limit, I'm jumping around a bit, but here's where limits help us answer these questions. Limits help us deal with undefined, okay? Because remember we were using limits for sums the other day to get rid of the bottom of a fraction we didn't like. It just gets infinitely large, so the fraction, if the denominator got infinitely large, the fraction goes away. But here, we're going to look at this a different way. Danny, I liked how you put that. We're going to look at this as a race between two rates. Okay?
Alright.
Slightly abusing the terms as well, as you put it, but we're going to roll with the way you put it. And here, I've got a top that's getting infinitely large. Infinity's getting squared. Infinity's getting multiplied by 3. I have a denominator where infinity's getting squared. What is the end result of this race? We did this end behavior. Remy, you were good at this game.
5 halves.
5 halves. This is how you find the horizontal asymptote of a rational expression. So in this case, this infinitely large thing on the top,
And it becomes like 0.
well, what happens is Remy liked to show these steps. That's why I kept saying he was good at it. The way to visualize what's going on is multiply top and bottom by 1 over x squared, which, after you distribute, becomes the limit as x approaches infinity of the 1 over x squared will cancel out with the x squared, leaving me just the 5. The 1 over x squared times the 3x will leave me 3 over x. 7 times 1 over x squared is just 7 over x squared. And on the bottom, I'll get 2 plus 3 over x squared. Now, remember when I said a limit is like a dog on a leash? When you let the dog off the leash is the important part. If I let x get infinitely large here, as large as I can imagine, I just get infinity over infinity. That's nonsensical. That's another indeterminate form like 0 over 0. That's problematic. Again, undefined, not a problem. It's a vertical asymptote or something. 0 over a number, just 0. Again, not a problem. Indeterminate form, big problem. Big problem. Those just can't happen. You've got to work around them. The way we've been working around it for end behavior is, if I let the dog off the leash in this step of the algebra, I get infinity over infinity. Can't have that. Perform a fairly simple algebraic trick. Now I let the dog off the leash, and infinity suddenly becomes our friend. Because 3 over something really large divided by something really large becomes something really small. 7 over something really large becomes really small. 3 over something really large becomes really small. And we are left with a limit, slightly different from saying an answer, but a limit of 5 halves. That's where this thing is headed. Remember what I say about limits. A limit is where you're headed. You don't really care if you get there or not. So this thing is headed to 5 halves. So I went on a little bit of a sidetrack than what I planned, but you've been using the idea of the limit to get rid of the indeterminate form of infinity over infinity already.
Alright.
We didn't use those words though, did we?
No.
Yeah, we called it end behavior of a polynomial. We did a couple of more of this with n instead of x on sequences and series, but you've been doing this. You've been getting rid of an indeterminate form. Let's go back. Indeterminate form 0 over 0. Why did I bring this up? Because over here, we were looking at this stuff. Okay, why did I bring up 0 over 0, infinity over infinity, any of it? Secant in red. Average rate of change between 2 points. Not a problem. Divide a y by, subtract y from y, subtract x from x. You get a slope. That's your average rate of change. That literally is the description of the car that goes exactly 50 miles an hour for 6 hours. Okay? But how precise is that? How useful is that? How often do things really do that in real life?
Happen.
Doesn't happen. In real life, we want to know what happens when the car hits the tree. And my problem with this is at the moment, I'm seeing since it hits the tree at a single point, it's a y minus the exact same y divided by an x minus an exact same x. That's 0 over 0. That's indeterminate form. We said over there that could be any number. Do I get to pick how fast I hit the tree? If I'm in a boxing ring with Mike Tyson at the exact instant of impact, do I get to pick how fast I hit him or he hits me? No, if I could, I'd box anybody. But I can't. So there must be a way to get rid of this 0 over 0 like we did before. So I'm going to erase this. This isn't helpful.
But what was the point of it?
What was the point of that? Okay, here's what we can do. We can't really find out what's going on at this instant directly. But we're going to do a new type of limit. Okay? All the limits we've done, I see those looks. All the limits we've done, we've talked about what happens when x is heading towards a point, right? Or when x is heading off to infinity. Or when x is heading to 0. Or when x is heading to 2, correct? This is a different type of limit. And a lot of math books just jump from the type of limit where you're just looking at what x is doing to this type of limit without acknowledging that this is a new idea. But here's what I want to know. I want to know what will happen if I start shrinking this interval. Not ask myself where is x headed, but what happens if this change in x? What happens if this starts to get smaller?
You're gonna get the f of x is gonna get smaller, or the y's. Sorry.
The y's will get closer together as well. You had the right idea. So as the distance between the x decreases, the distance between the x will also decrease. And eventually, we'll be looking at a smaller secant. I'm not going to draw it because that would become a mess. A smaller secant line, a smaller secant line, a smaller secant line. And the question is, how close to that can we get? How close to a tangent line can we really, really, really get? So what I'm interested in is...
Will we eventually stop caring? Or
maybe. Sort of. Yes. I'm interested in the limit as the x's get really, as the distance between the x's gets small. So this is new.
It's not, is it like an asymptote at all? Or?
Yes, but not, yes it is, but that may not be the most useful way to think of it right now. Because with asymptotes, you're always thinking about y getting close to something as x goes somewhere. Or you're thinking about y headed to infinity as x gets close to a number. But here, this notation is the important part. This is not about where x is headed. This is about the distance between two x's shrinking. Different type of limit. Now, what we care about is the slope. I want the slope of this secant line to get really, really close to the slope of this tangent line. All right? So I want to know what happens as delta x approaches 0 of my y values. I'm going to use this notation. What happens? Danny, you said it. These y values get closer together as the x values get closer together. But I'm going to write the y values the way I wrote it here. F of x plus delta x minus f of x. Here's x, here's f of x. This is x plus some more x. This is the y that corresponds to x plus some more x. And on the bottom, I'm just going to put delta x.
Wait, so is it the secant that's shrinking when you do?
Yes. Here's the slope of the secant line in red. Corresponds to this red line.
Yes, that's what I thought.
Right. What I'm looking for is the slope of this tangent line. This statement is sort of a hope at this point. It's not. It's called the limit definition of the derivative. But it's a real thing. But right now, in our hearts, this is kind of a hope that if we take this delta x and make it smaller, that's what the limit as delta x approaches 0 is. If we take the distance between these points and make it smaller, the distance between the y's will shrink, and we'll go from talking about a secant to talking about a tangent. Now, to really be talking about a tangent, what's happening in an instant? What is the rate of change at this one exact point? The distance between these x values would have to shrink to 0. If we just do that, well, what happens? If we let this dog off the leash, delta x becomes 0, right? Then we'll just have f of x minus f of x. What's that?
That would be 0 over 0.
Right,
Which
we
would
would
be
get-
indeterminate form.
Awesome. We would get 0 over 0, and I'm intentionally putting,
But why did you slash to the equal?
I'm intentionally putting a slash through the equal sign because it can, it has to equal 0 over 0 if we let the dog off the leash here, but
You
it
don't
can't.
want to?
The fact is, if you're feeling visual, you can look at this. It can't be any number I choose. I mean, look at this for a second. We're talking about a slope of a line that barely touches the function. Just intuitively, it seems like if I just want to barely touch this function with a slope, a secant line, doesn't it look like it should be positive here? I mean, does this look like a slope that barely touches this curve at one point?
Yeah.
Well, it crosses
Well,
it
I mean,
at
it
one
crosses
point.
it, but like it doesn't.
Does this look like it describes what that curve is doing? Because that's what we're looking for. We're looking for something, I mean, a secant line tells you the average of what this curve did
It
over
goes
this time.
through the thing multiple times if you put
I mean-
it like that way.
Yeah, I mean, for one thing, if your function is increasing, your rate of change should probably be positive. So I'm pretty sure this won't work. So it doesn't look to me like an indeterminate form means I can pick anything. And it doesn't look like I can pick anything that will really describe the rate of change at that instant on that curve. There has to be something other than 0 over 0 that works. Now, we can make guesses at it. We're going to start, well, first off, any questions on this? I know it's probably lots of questions on this, but any specific questions on the notation, or the idea, or the fact that the problem with finding an instantaneous rate of change represented by a tangent line, as opposed to an average rate of change represented by a secant line, is that we shrink this interval, we make it a limit, and we get 0 over 0, which cannot happen. Do you get what the problem is here?
Yeah.
All right, congratulations. This is a problem that stumped mankind for thousands of years. The solution's coming up. I'm just going to write real quick that this means instantaneous rate of change. And I'm going to take a quick picture of this because, believe it or not, this is about the most neatly I have ever drawn the setup for the derivative. What do you think, Tyler? How does this compare to last year?
That's pretty nice, actually.
I think
Whoever's watching this is probably really confused why Tyler's here.
Well, I don't think they need the full backstory, but yes. They can just wonder why someone who just took the AP exam is sitting in a class learning about the derivative for the first time.
He actually failed pre-calculus.
No,
And now he has to retake it even though he probably passed the AP exam.
don't even joke. All right, okay, so that'll be useful for the people who aren't here today. All right, now I'm going to erase this, and we're going to bring up a specific situation that we are going to...
Wait, so is that like the formula you use?
That's a formula we use. I'm going to leave that on the board for a second, this limit. And we are going to do this 2 different ways over the 2 periods we luckily have. But first, I do need a volunteer to go public for a moment. I normally don't do this, but I am going to punch someone in the face. Tyler, you volunteering?
Wait, I have a question.
Before.
I
Yeah.
know you probably mentioned this, but what does the M stand for again?
M is just M for slope,
Oh, okay. That
like
makes
M in Algebra 1. Okay, Tyler, welcome. I need to punch Tyler in the face for a moment. I need to do it twice.
Sounds good.
Are you guys ready?
Yeah.
All right. Take a deep breath, relax. Okay, so I think I did this for Joey last year, didn't I? All right, okay. All right, 2 different punches. I'm going to punch them twice. We'll set this up now, we'll solve it 4th period. But we'll start to solve it this period. Okay. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Okay? That was 1 punch. Wasn't very dramatic for the punch. Okay? Think I get a better view from here?
Yeah, you couldn't see your fist going on.
Oh, okay, all right. How will this be? This is a good starting point?
Just Tyler's kind of standing where your fist would be.
Okay, here,
Because
come over
of
here a
the-
sec. How's that?
Yeah, it's better.
All right, what's that subclave? Okay, now, notice on that time, my fist moved about 30 about 30 inches over 6 seconds. Correct? Okay, and it seemed to move at a constant speed. That wouldn't have been very exciting to graph or talk about. Let's talk about this situation. I'm going to do this. I'm going to do a second punch with the same average rate of change. Same average rate of change. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Okay, so once again, thank you, Tyler. Good man. Well done. The second punch, I also moved my fist about 30 inches over a 6-second time interval. Was there any difference between the two punches?
Yeah, one went a lot faster than the other.
Over a much shorter time interval.
Yeah.
Okay. The first punch. No, I'm going to do this one in red because this is going to be our secant line.
Color blood.
Thank you, Danny. I hadn't thought of that. Okay, so the first punch. Start here at 0. This will be time in seconds. This will be displacement in inches. We started at 0, 0. After 6 seconds, we've gone about 30 inches. A constant rate of change on a position graph should be represented by a line. This is the point 6, 30. And what's the slope of this line? What's my rise over run? What's my delta y over delta x? What's my f of x plus delta x minus f of x over delta x?
What?
What's the slope of this line?
It seems to be,
Don't go visual because
Five.
I skew. Yeah, 5. I changed my units here. So the slope of this line is 5. And it's 5 inches per second. And if I had actually connected with Tyler on this punch, any point in that 6 seconds, he would have felt a 5 inch per second punch, right? And that wouldn't have been so bad. I hope. He doesn't seem like he's that sensitive. Any questions on how this describes what happened on the first punch? Just my fist moving at a nice steady pace,
yeah.
right? Okay, Remy, you good with this?
Yeah.
All right. Now, the second punch. This one was a little bit more interesting, I think. On the second punch, this one I need to actually put in a little bit more detail. Okay, what did I do for the first 4 seconds on the second punch? Do you remember? For the first few seconds, what did I actually do with my fist? As Dan, take a moment, write this down, but what was I doing on that second punch for the first part of my time interval?
You were going the same speed you wanted first.
Now the first punch I did.
Well, no, at the very beginning of the second punch, you went 1, 2, and then you went 3, 4, 5.
Actually, yeah, I went on 4. But for the first few seconds, I wasn't actually doing anything.
Oh, okay.
It was just sitting still. So I just stayed here at a position of, that's what I meant to do anyway, was stay still for the first 4 seconds. Now, I've timed this in the past, and I've thought about this a bit, and turns out I covered that 30 inches in about a tenth of a second. I haven't done it lately with modern tech, with, watch, someone's going to go down and slow down the frames and find out exactly what I did. Now, when you're throwing a punch, your goal is not to move at a constant speed. Your goal is to actually accelerate. Okay?
So this is like physics, but math stuff.
You're not wrong. This is going to tie into a lot of stuff we did in physics. So what I'm trying to draw here, and I apologize for it, is a parabola. Because if you're talking about something that's accelerating constantly, you know, a parabola is a good bet. It's not perfect because I was accelerating at the beginning, I'd make contact, and then I was actually decelerating at the end. I'm not going to deal with the deceleration part. And then for the last 1.9 seconds, my fist just sat there as I finished my count. So this punch had nothing going on. Boom, quick acceleration for a tenth of a second, nothing going on. Okay? Can I erase this first punch? It's kind of boring me.
Yeah.
Need more board space. You guys remember this, right? It's just a straight line.
Yeah.
Okay, I'll add it in green to that one if we think it'll help. But now, let's think like physicists for a second here. Here's that first punch. This board is looking very comfortable. Okay. If I look at the whole 6-second colorful, that's what I meant. This board's looking very colorful. If I look at the entire 6 seconds here, on both punches I have the same average. But do you think I was hitting Tyler on that second punch at 5 inches per second?
No.
Think he would have felt a difference maybe?
Yeah.
Alright, now, rates of change are always represented by slopes. Okay? So on both punches, the average rate of change was 5 inches per second. The difference is on that first punch, the instantaneous rate of change along a line is always just the slope. If I'd hit Tyler anywhere over those 6 seconds, he was just going to feel a 5 inch per second impact. The average rate of change and the instantaneous rate of change are the same thing on a line. That's why in Algebra 1 you didn't have to know the difference. Does that make sense? If something's tooling along at a constant velocity, its rate of change is always just that velocity. The second punch, we would have to represent this with a piecewise function. And that piecewise function is, let's see, first it was 0 for the first 4 seconds. For the last 1.9 seconds, I was 30 inches from where I'd started. So the question is, what happened in between? What was going on from 4 to 4.1 in that 1/10 of a second? Think we can find out what that punch was? If I say it's a parabola that starts with a vertex at 4, 0, and ends at 4.130. You guys ready for a quick review? That's the last thing we'll do before we pick it up again in the 4th period. I'm going to leave that there. Take another look at this board. Okay. Let's see what's going on here. The punch, I said, can be represented by a parabola, because I was trying to accelerate constantly. The vertex of that parabola was 4 seconds in, and my fist had moved 0 inches. Another point on that parabola was the point 4.1, 30. Anybody here remember vertex form of a parabola? I know, still take a moment, get that in. I don't mean to rush. But there is a vertex form of a parabola has all these qualities that I always talk about in functions. It looks something like y equals a x minus k squared plus h. Does this look familiar? This part here? Remember all the stuff we did with k's and h's and moving functions around? It's a parent function of a parabola, maybe multiplied by something to make it more narrow or more wide. That's your vertical compression. I'm sorry, that's your horizontal stretch. Vertical compression would be in here, but we're not going to deal with that. This is left to right counterintuitive motion. This is up or down intuitive translation of that function. Well, what do we know about this? If we know the vertex, we can fill that in. So this is definitely y equals a times x minus 4 squared plus 0. How do I know that? Because on a parabola, flip the sign on K, don't change the sign on H, plug in your vertex. That will be the coordinates of your vertex. How am I going to find this A value? I plugged in the vertex. How am I going to find that coefficient?
Oh, you plug 4.1 and 30.
Excellent, Remy. Knew I could count on you. So put in 30 for Y, put in 4.1 for X. Don't worry about the plus 0. So this leaves me with 30 equals A. 4.1 minus 4 is 0.1 squared. Let's see what I'm looking at. 0.1 is the same as 1/10, correct?
Yeah.
Okay, so I square 1/10, and I'm going to get 1 over 100, right? Did this part a little bit quickly, so please double check me.
Wait. Oh, never mind.
Okay. I apologize for doing this algebra a little bit quickly. I just want to get one step further. Am I good up here, Remy?
Yeah.
Okay. Now I multiply both sides times 100, and A is going to be 3,000. So this tells me that the parabola that describes my punch is y equals 3,000 times x minus 4 squared. That should work. Give you a moment to stare at that. That's really not the important part today, but I did want to review that. So I can now fill in my piecewise function and say that here, if I'd left myself enough room, I could fill in my piecewise function. Almost done, Danny, for now. X minus 4 squared, and that's from 4 to 4.1. Any questions on this? I get that the big picture is a little bit fuzzy right now, but any questions on the details? All right, we're going to pick up right from here at 10:55. Don't be late. And everyone else is going to have some serious viewing homework tonight.
Wait, everyone else except us?
Well, if you want to watch it again, you can.
Yeah, I mean, we just